Hello, welcome to Chapter 15 on Waves and Sound. In part 1 of this video lecture, we will look at an introduction to waves. So this part of the lecture, we will look at properties of waves and some of the wave mathematics, some of the equations that describe waves. And in part 2 of this video lecture, we will be dealing almost exclusively with sound, and we'll also look at wave energy and intensity. Let's start by looking at the properties of waves. So imagine doing a little demonstration like this. Suppose you have a rope that's attached to the wall or a tree or something over here, and every once in a while you give the rope a little flick of the wrist to create a pulse. What happens is that pulse, which is a wave, travels down the rope, and you can see it propagating from left to right. Now, one thing, if you look at this, it looks like the rope is actually moving to the right, but it's not. In fact, the material of the rope only moves up and down, and we can see this more clearly by looking at this animation right here. Imagine taking the rope and go continuously flicking your wrist up and down like this. This is kind of shown in slow motion here. So you're creating a sequence of pulses, and these pulses move down the rope like this. What's shown here on the rope are little, let's say, like beads attached to the rope. And look at there's a red bead here, 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 and here. And notice that if you watch one of those red beads, all the red bead does is go up and down. It does not move left or right. And this is the characteristic of what is called a transverse wave, which we will look at a little bit more in the next slide. But so what is actually moving then? If the material of the wave is actually not moving down, the rope, what is transferring? Well, what is actually transferring is energy. The other thing I'll point out here is you can see that we can define the wavelength of this wave as the distance between two consecutive peaks. And we'll talk more about the wavelength and period and frequency of the wave a little bit later. So our definition of a wave is a traveling disturbance through an elastic medium that transmits energy. So in this case, the rope is our elastic medium. And what an elastic medium means is that it's a material or a substance that is basically stretchy. And most materials are elastic. Remember, we looked at this earlier in the course when we talked about Young's modulus, and even materials as hard as diamond do have elastic properties. So waves can travel through pretty much anything. They can travel through a liquid, solid, or even gases. The disturbance is, in this case, it's a single pulse. In this example here, the disturbance is a whole sequence of pulses that are sent down the wave at regular intervals. Another example to show some of these features is when we think about waves in water. So if we think about a wave on the ocean or a lake that's moving, this is showing 3 different snapshots, and let's say there's something floating in the water right there. It might be a jellyfish or an empty bottle or something like that. What happens as the wave travels through is the object floating in the water just moves up and then comes back down to the water level. And the same can be said for all the water molecules. They are not moving with the wave. The wave moves through the material, which is very evident and easily seen up here in these examples. Waves can be characterized into 2 different types. One is called transverse and the other is called longitudinal. So in a transverse wave, the oscillations or the vibrations are perpendicular or transverse, those mean the same thing, to the direction of wave travel. So here's a couple examples. This is a spring or a slinky, and you can see the hand here is creating waves, but this is what we saw in the previous slide. The disturbance in the slinky is just going up and down. The wave is traveling left to right, and the disturbance is going vertically, up and down, transverse to the direction. Here's our rope again that we saw on the last slide. Again, the waves are moving horizontally, but the material in the rope is moving up and down. It's not moving back and forth. Now, a different type of wave is called a longitudinal wave, and that's the case where the oscillations are in the same direction as which the wave travels. So again, taking our slinky here, it's easy to create a longitudinal wave by pressing or pulling on the slinky here to create a pulse. And you can see the region of compression here actually travels down the slinky. But again, the slinky material is just vibrating back and forth. The material of the slinky is not traveling with the wave. The wave is traveling through the slinky. The wave always travels through the medium. The medium does not travel with the wave. But the key thing here for a longitudinal wave, again, is that the material, the medium, is vibrating back and forth in the same direction, horizontal, as the wave travels. Another classic example of a longitudinal wave is a sound wave, which is the subject of part 2 of this lecture. So this is a tube here filled with air. So every one of these black dots represents a molecule of air. And this plunger here is moving back and forth and creating these compressions of sound waves. When it piles up, it looks like it's piling up the molecules in front of the piston when it moves to the right. And then we can see these compressions moving at the speed of sound through the material, through the air. But again, it's important to note that any given molecule is not traveling from left to right all the way across the tube. It's just going back and forth. So for example, take a look at, there's 3 molecules. There's one red one here, red there, and red there. Watch what happens as a wave travels through it. The molecule goes to the right, it snaps back to the left, and then it goes back to the right, and back to the left. It's not going anywhere. It's not moving down the tube. It's just vibrating or oscillating back and forth in the same horizontal direction as the wave is traveling. So this is another classic example of a longitudinal wave. Waves can also be classified as either mechanical waves or electromagnetic waves. And in this, in Physics 101, we are going to be talking only about mechanical waves. Mechanical waves travel through a physical medium, which is either a solid, a liquid, or a gas. So for example, if we wiggle a string, the string is the physical medium, all right? It's a solid material. It's an elastic material. A sound wave that we just saw, that travels through a gas. Typically, sound also travels through liquids and solids, but when we think about sound traveling through the air, that wave is traveling through the air itself, the gas of the air. And then ocean waves, of course, are waves that are traveling through a liquid. Electromagnetic waves are very different, and we're not going to study those in this course. They will be the topic of Physics 102, but interestingly, electromagnetic waves can travel through a vacuum. They don't need a medium to propagate through. So without any physical medium, this is a very different type of wave. And these waves are due to oscillating electric and magnetic fields. Again, though, this is not the subject of this chapter, so we won't be talking about electromagnetic waves at this point. All waves have certain characteristics that they share with each other. And so that's what we're going to look at here. So the 4 main characteristics of any wave are amplitude, wavelength, period, and frequency. So the amplitude of the wave, this is something that we saw in the previous chapter on oscillations. It's the maximum displacement from the equilibrium position. So if this is a picture or a snapshot of a rope that has waves traveling on it, This is the equilibrium position here, which would be the rope held tight, where it's not vibrating at all. So the amplitude is measured from the equilibrium position up to the top of this crest here. Or we could likewise measure it from here down to the trough for this particular wave. But it's wherever there's a maximum distance from equilibrium up to the top or bottom of a wave, that is the amplitude, and that is measured in meters. We already saw a little example of the wavelength. The wavelength is the distance between two peaks or two troughs. So in this example here, we would measure from one crest here to the adjacent crest here, and this distance is called the wavelength. And the wavelength is usually designated with the symbol lambda. This is the Greek lowercase lambda symbol, and wavelength is a distance, so it is measured in meters. The period of a wave is the length of time for one cycle to pass the same point. So if we look at this wave here, so this is you can think of this as a rope, and we're wiggling one end of the rope, and we're making these wave pulses travel down the rope. If we were to, let's say, put our marker right here, and we were to measure when one peak comes, like right now we start our stopwatch, and then when the next peak reaches right now, we would stop the watch. That would be the amount of time for one complete cycle to pass by our marker there. And so that is what we mean by a period. And the unit of period is second because, of course, period is measured as a unit of time. The last characteristic here is the frequency of the wave. That's the number of wave cycles per second. And again, what we would do is we could pick a point, for example, with my pointer here, and what we would do is we would count how many of these peaks come by every second. All right, if this wave was moving really fast, like a sound wave, we might see several hundred peaks streak by during 1 second, and that would give us the frequency of the wave. So the units of frequency are cycles per second, and that is called a hertz, which is abbreviated uppercase H, lowercase z. And by the way, frequency and period, we saw this in the last chapter, have a reciprocal relationship. The frequency is equal to 1 over the period, t, and likewise, the period, t, is equal to 1 over f, 1 over the frequency. The last thing we're going to do in this part of the video lecture is to look at some of the equations that describe the properties of waves. And in this course, we're going to keep things pretty basic and simple. We're not going to get into a lot of the detailed mathematics of waves that you will see in more advanced courses. So the first thing we're going to talk about here is the speed of the wave velocity. The way to figure this out is actually quite easy. Remember that one wave cycle has a length of one wavelength. Okay, that's the definition of the wavelength. And we know that each cycle goes by in one period of time, and period is designated as the uppercase T. So remember from kinematics, the study of motion, that velocity of an object is equal to the distance it travels divided by the time it takes. So if we let our distance be one wavelength that the wave is going to move, then we know the period the time that takes is one period t. So the next thing we can do here is remember that period t is equal to 1 over the frequency. And so we have 1 over f down here in the denominator of our fraction. So this f comes up to the top, and we end up with our formula for wave velocity. Wave velocity is equal to the wavelength, lambda, of the wave times f, which is the frequency of the wave. So it's a very fundamental and simple relationship here between the speed of a wave, its wavelength, and its frequency. So let's look at an example. Ocean waves that are 2 meters tall hit the beach every 5 seconds. The distance between the waves is 40 meters. So 4 questions here. What is the amplitude of the wave? Well, the amplitude here would be the height of the wave. So that's 2 meters. What is the period of the wave? Well, we were told that the waves are hitting the beach every 5 seconds. So that's the period. T is equal to 5 seconds. What is the frequency? Well, remember the frequency of a wave is equal to 1 over the period. So it's 1 over 5 seconds, which is 0.2 hertz. And finally, what is the wave speed? Well, wave speed, V, is equal to lambda F. So lambda is the wavelength. So that's the distance between the waves. That's the distance between two peaks or ocean waves is 40 meters. So that's our wavelength, lambda. And our frequency, we just got that up here, is 0.2. And so 40 times 0.2 turns out to be, that should be, this is a typo here, that should be 8. I'll cover up the 0 point. It should be 8 meters per second is the speed of our wave there. The last thing we're going to look at in this part of the video is the wave speed on a string. So I'm not going to show you the proof of this or the derivation. It takes a little bit of work and effort to derive this result here, but the result is relatively simple. It says that the speed of a wave on a stretched string or rope or cable is equal to the square root of the tension of the string divided by the linear mass density of the string. This symbol here is called mu. That's the Greek letter mu, and it represents the linear mass density of the string, which is equal to the mass of the whole string divided by the length of the whole string. And this, so it's m over L. This gives us the number of kilograms per meter of string. So what this tells us is that a tighter string will result in a faster wave. And this is because when there's more tension in the string, the forces are greater and it tends to accelerate the pieces of rope more quickly. Also, down on the bottom is the linear mass density. What this tells us is that the heavier the string or the rope, the slower the speed will be. And this makes sense too, because remember, heavier objects are harder to accelerate. So when we have a heavier string, that's going to slow down the speed of this string or rope. So I'll leave you here with a video demo done by another professor that will show you these characteristics of the speed of a wave on a stretched rope.
I have here a long rope, and on one end it's attached to the wall. And I'm going to stretch it out, and many of you have probably done this with a rope or maybe a garden hose. And if I stretch it and give it a flick with my wrist, I can make a wave that moves down the rope. So let's do that. Now you see a curious thing. When the wave gets to the other end, it in fact reflects and comes back. You notice that? And in fact, when it hits my hand, it reflects again, and the wave goes back and forth along the rope. Now, you've probably all done that, and that's familiar to you, but you may not have looked carefully at what happens to the wave when the rope has very little tension in it, as it does now. You see the wave moves relatively slowly. It takes a long time to get down and come back, but if I pull hard on the rope, give a lot of tension, the wave moves much faster. And in fact, the speed of the wave is proportional to the square root of the tension in the rope. So that's a familiar idea and probably is of no great surprise to you. But I want to show you another demonstration that involves waves traveling on a rope. You see over here we have two ropes. The upper rope is a 1/4 inch rope, very small, and the lower rope is a 1/2 inch rope, much bigger. And these ropes are under exactly the same tension. How do I know that to be the case? Because down at this end there's a pulley, and the rope goes around the pulley. So they're being pulled with the same tension. But one rope is a light rope and the other is a heavy rope. Now who thinks the wave will travel faster on the light rope on the top? Who thinks it will travel faster on the heavy rope on the bottom? A few people. So most people think the light rope will have the greater wave speed. Now, to make a wave on the rope, I have to somehow start the wave at the same time on the two ropes. The way I'm going to do that is to take a meter stick, and I'm going to hit the two ropes at the same instant. Now, you notice Mr. Lovell has put a couple of index cards on the rope down at the other end. There's a red one on the top and a blue one on the bottom. And what you're going to see is as the wave moves down there, those cards are going to jump off the rope. And the card that jumps off first, obviously, is on the rope that has the greatest speed. So don't watch me. Watch the cards down there, and I'll tell you when I'm going to hit it. 1, on 3, 2, 3.